Hi, I'm Mohammadreza Behrouzi. We are proud of ourselves that you watch our videos and we can make a small contribution towards your knowledge improvements. These videos that we have uploaded on our website or on our YouTube channel consist of notes and real case examples from our last projects. Those projects were performed by a team of professionals and experts. Therefore, by watching these videos, you can gain tremendous amount of knowledge and experience by which you can design your process units, your plants with highest safety. You are our only sponsor. So if you enjoyed the video, at the end, hit the like and subscribe so that you can get informed about our latest videos. In this episode, we're going to explain what interlock and logic diagrams are, what the differences between interlock and logic diagrams are, and how we can create interlock and logic diagrams for rotary equipment and process plants. Interlock and logic diagrams are one of the most important documents which should be created during basic design and later developed during project phase or detailed engineering. Process engineers as well as instrumentation engineers should place a great emphasis on the creation and accuracy of interlock and logic diagrams during detailed engineering, because otherwise it might have some high consequences for the plant or the equipment itself. And you might wonder in your mind as process engineers, you might wonder and ask this question: why should I learn logic diagrams? Interlock diagram, you might say that interlock diagram belongs to process engineers, whereas logic diagrams belongs to instrumentation engineers. Then why should I learn logic diagram? Of course, you're right on the part that interlock diagrams belongs to process engineers, and during a startup, during let's say project phase, process engineers or operators who are working in control room just use interlock diagrams in order to perform their tasks and start up or shut down different process plants or let's say equipment such as pumps or turbines. But but based on my experience, it would give immense power to the process engineers if they learn how to use logic diagrams. And besides, and in addition to that, they can provide consultancy to the instrumentation engineers. I've had extensive experience working with interlock and logic diagrams. There is a point in project phase at which process engineers should collaborate with instrumentation engineers in order to perform function tests and check each and every loop used in control systems. And if during that period process engineers know how to use logic diagram in addition to interlock diagram, the work can be done in a much faster and in a more accurate manner. Therefore, I highly recommend you learning logic diagram besides interlock diagram. Now I'm going to start the session here, And as I stated before, this session is just devoted to rotary equipment such as pumps. There are other following videos in which I explain and develop interlock and logic diagram for different equipment such as fire heater, separators, and turbines. You can go to our websites and watch those videos after watching this video. But before going further and elaborating upon the pumps, interlock and logic diagram, it is really important to notice and take into account the following notes about logic and interlock diagrams. In a process plant, action performed in the IS are called IS groups, interlock safety, and action performed in the DCS are called I groups or simply interlock. As process engineer, you might have worked in some petrochemical or refinery plants. We have two systems in order to control and protect the plant. DCS is mainly used for controlling purposes, while ESD system is used for protection and shutdown of the plant. So some of the equipments are more important and require more protections in order to prevent any further damage. Therefore, their shutdowns, their interlock, their logic diagrams are placed and written down in ESD system. But some of the equipments, such as motors for the pumps or the pumps themselves, are less important. It doesn't mean that they are not important. They are less important. And of course, the purpose here is for controlling purposes. Controlling plays an important part here. Therefore, their interlock is written in DCS system rather than ESD systems. So we have two kinds of interlocks, or let's say interlocks: IS groups and I groups. Action performed in the IS are called IS group, and action performed in the DCS are called I group. Due to a considerable higher cost of IS than DCS hardware, consideration has been given to define which actions are to be performed in the IS systems and which actions are to be performed in the DCS. In order to establish guidelines for the distinction of those actions, the following rules are applied. Trips in the IS groups are generally based on 2 out of 3 votings. IS groups must protect personnel against safety hazards, critical plant equipment, and unit trips which will result in a significant production loss when initiated. As I have stated, IS groups are used for important equipment, let's say critical plant equipment, or when personal matters and personnel against safety hazards, to protect safe personnel against safety hazards. Whereas I groups must protect auto start and stop of motors, avoidance of PLC relief, and switching of operating mode. These are important, but less important than critical plant equipment, less important than personnel against safety hazards. Therefore, they can be placed in DCS systems, and this equipment can be placed in ESD systems, and therefore IS groups belongs to those systems. As I stated, the main root for difference between ESD and let's say between IS and I groups is the cost. IS groups are more costly because they require and demand hard work. Now, I just wanna jump into the main issue and start instructing how we can create interlock and logic diagram for pumps or rotary equipments. Here, before before creating interlock and logic diagram, we should have a clear understanding of the equipment. What is the function of this equipment and how it performs its tasks. Here, I'm going to show you a typical example of a typical pump. In every refinery, plants, and petrochemical plants, we have reflux pumps. And what is this reflux pumps? Every refinery plants, every petrochemical plants needs purifications of the products. And in order to distillate the products, we need a distillation sections. And in those distillation sections, each distillation column requires the reflux flow so that it would function properly and the purification will be done in the utmost manner. In order to maintain the reflux flow to the column, we need some pumps as reflux pump in order to pump the reflux flow to, for example, 70-meter height, or let's say 50-meter high. Therefore, those reflux pumps are extremely essential to the function of distillation columns. They are typical pumps, as you can see here. Here is the reflux pump, here is the reflux drum, and here is the reflux pump. We have two pumps here, pump A and pump B. And here is the line to the suction of the pump, and here is the filter. As I have stated, the function, the duty of these pumps is to maintain the reflux to the distillation tower. But as I have stated, in order to protect the equipment, or here to protect the pump, or let's say to have a overall view to protect the process plant, I should create an interlock diagram in order to facilitate the shutdown procedure, the startup procedure for the pump. So all of these are done in an automatic way, are done automatically. Then, as process engineers, should create a document for the description of the cause and effect, or let's say interlock diagrams. Your description should contain two parts: the causes for the interlock safety or the IS or interlock groups, and the consequences. Here we're going to focus on the description of the interlock for these pumps. This pump is one of the important pumps in our plant. Therefore, it is categorized, the interlock to this pump is categorized as IS groups: three-puff stabilizer column reflux pump. Two parts, as I said. The causes for Intel IS-56 trips are manual panel trip, low level in stabilizer column accumulator, or let's say reflux swarms, low level. For most pumps interlock that I have been involved in creation of them, and there are two or three causes which can stop the pump. Manual panel trip, there is a button in the console of the control room, and this button is pushed by the operator, and of course it is up to the operator, it is the decision of the operator to decide the time to pushing the trip button. Sometimes there is a fire scenario, sometimes there are other reasons that process operators decide that this pump right now should be stopped, even though the level in the reflux drum is in normal conditions. Another reason, another cause which trips the pump is the low level in reflux drum. As you know, low level in reflux drums means the further cavitation in the pump and further damage to the impeller and the other parts of the pump. Therefore, in order to prevent all of these consequences, we create interlock diagram. And the following actions are carried out automatically. Stop a stabilizer column. It signals to the substation and stops the motor of those pumps, pump A, and similarly the same signal goes to the pump B motor. So how to create interlock diagram and how to read interlock diagram for this pump. Here is a typical example of the creation of interlock diagram for this specific equipment. Normally we use AutoCAD in order to create such interlock diagrams and let's say logic diagrams. But here, for the training purposes, we just focus on the interlock and logic diagram and how we can create them and which nodes should be taken into account when it comes to the creation of interlock and logic diagrams. But later you can go to my websites and watch those packages of interlock packages devoted to interlock and logic diagram, and you can see how I use and manipulate AutoCAD to create such documents and diagrams. So as I have said earlier, there are two causes for the trip of the pump. The manual trip here and the low level in the reflux drums. Here this part shows the cause of and depicts the cause for the low level in reflux drums. It contains 4 parts. In these parts, you should describe the cause here. In this part, you should name the tag of the cause. This part should refer the process engineers to the piano ID and to the page of piano ID. And here is the description of the first cause, and here we have the manual trip. Of course, you can place manual trip in this place, or you can simply, like I've seen in most refineries do this, you can add another line like this one here and add empty in this way, or manual trip in this place. Most of them are correct, so it depends on the philosophy of the engineering or licensor groups to decide the typical diagram for interlock and logic diagrams. The third part is the delay time. As you can see here, it is 0 to 10-second delay time. What is the purpose of this delay time? Sometimes, sometimes the level of liquid in the reflux drums is in normal conditions, say for instance 70%. But unfortunately, the level transmitters shows different value, shows a wrong value, say 26%, and subsequently send this value to the control room. If I don't place this delay here, it is just gonna trip the pump and causes some abnormality in the plant. But if I place this delay time, I can prevent such occurrences. How? As I stated, sometimes the value shown by the level transmitters goes wrong in just 2 seconds, 3 seconds. In fact, the value shown by those level transmitters are fallacious or wrong just for 3 seconds. So I create a 10-second delay time so that the level transmitter would be able to correct itself, and after 3 seconds or 5 seconds it would be able to show the correct value and subsequently signal the correct value to the control room, and such abnormalities would be prevented. Therefore, that's the function of delay here, delay time here. It is a simple delay. I've been involved in many, interlock diagrams for rotary equipments and process plants. For instance, I've seen that one of the great leading companies in production of the compressors in their interlock diagrams uses four types of uses four types of delay time for different purposes. But here, for process plants, it is just a delay time. Now we have the reset here. I'm going to explain the function of reset here when I explain the logic diagram. In that time, you can fully understand the concept behind reset for interlock and logic diagram. And this part is the consequences of the interlock or IS groups. The signal, the consequences, or the following actions are the stop of the pump. This part contains 5 parts: the tag of the solenoid, the description of the action, the tag of the motor which should be tripped, and of course the piano ID and the page of the piano ID. So far we have explained that the interlock or IS for a typical pump consists of 3 parts: the causes such as manual trips and low level in reflux drums, the following actions or the consequences here, and some accessories to the interlock such as reset and delay time. We have explained the function of delay time, manual trip, and different parts of these sections and these sections. Now we go further in order to show how to create logic diagram from interlock diagram. Whenever I want to explain the differences between interlock and logic diagram to some of my fellow process engineers or my colleagues, I explain it in this way: that interlock diagrams are virtual mode, while logic diagrams are in fact reality of those interlock diagrams. Another mindset, another perspective toward these diagrams are that interlock diagrams are developed especially during basic design, whereas logic diagrams are developed and created during project phase or detailed engineering. In fact, it makes those interlock diagrams more detailed, and that is the logic diagram. As it is shown here, there are some elements in the logic diagrams. For instance, this one, let me zoom in. This one is called set and reset, or simply some people say that flip-flop. This one is and or element. This is maintenance override switch. These are the causes of the trip. And here is the reset, and here are the consequences, and you can see some binary values such as 0 or 1 in this case. But what are the meanings of these binary values? What is the meaning of flip-flop and how it functions? What is the meaning of maintenance override switch and how it can help us to better protect the equipment? So here I'm going to show you a legend by means of which we can describe and detail out the function of these elements. It is a typical legend for that you can find at the first page of each logic diagram, regardless of the vendor, or let's say the licensor of the equipment or process plant. It contains different parts. Here is the symbol of the causes, or the, let's say, final elements. For instance, final elements for solenoid valves is shown by this one, or for pumps, final elements for pumps is shown by this symbol, or calculation conditions. When we want to indicate that some calculation conditions, there are some calculation conditions in the loop, we can use this symbol. But let's focus what we need as process engineers and what is important. Here we have AND group, AND element, or element. After describing flip-flop or set memory or reset memory, I'm gonna describe the function of AND and OR element. Flip-flop or set memory contains of different elements itself. Set, which is indicated by S, and R, resets. Now let's describe this. Output C and D are always opposite. For instance, when it is 1, it is 0. Right now, I just want you to focus what I explain, and if you can't understand what I'm saying, it doesn't matter, because I'm gonna use two examples in order to show you how these definitions can be put in practice and what they mean in practice. So don't worry for now, just listen to what I say. C and D are opposite of each other. When C is 1, this one is 0. Imagine that A is 1. When 1 enters this one, If I get a value from this line, it means that the output would be 1. But if I don't draw any line here and instead just draw this line, as I said, since it is 1, it becomes 0. Or when the b equals 1, d becomes 1. So what we have learned, let's review what we have learned. C and D are opposite of each other. When C is 1, this one is 0. When I equal A to the value of 1 and draw this line for my any purposes, the C would be 1, but for another equipments, I prefer to use D instead of C and don't draw these lines. Since normally this line would be 1, and instead I draw this line, and this line based on principle is the opposite of this one, and this one was 1, so this one becomes 0. As simple as this one. So in other way, if it goes directly like this one, it becomes 1. But if it goes down, it becomes 0. As simple as this one. And for AND group, when the input is 1 and the input is 1, the output would be 1. But if one of the input is 0, the output would be 0. So if I want to get the output equal to 1, both of the input should be 1. And how about OR? When one of the input becomes 1, the output would be 1, regardless of other inputs. For instance, we have 5 inputs to the OR elements, and one of them is 1, but other types are 0. The output would be 1. And here is the negation, input negation. What does it mean? If I get it's shown by this symbol, a small circle like this one. If I equal the input to 1, it negates, it reverses the value to 0. Or if this one is 0, it negates the 0 and reverses the value to 1. That's the function of this one. Now, to better understand the logic and how it should be created, I'm gonna transfer the file to the Paint and show you in a bigger picture how it works and how we can create such diagrams. As you can see, logic diagram is just the interlock diagram, but in a detailed manner. How? You can see that we said that it is the manual trip, it is the low level in reflux drum. Here contains the in fact the causes for the trip, and here are the consequences, and here the calculation behind the IS groups that was not shown here. Here flip-flop is just lies at the back of this one that you don't see in interlock diagram. So it is just interlock diagram in a more detailed way. Now I want you to look at the flip-flop and element and different symbols for different functions from different perspective that I just show you. and I'm going to show you in practice and in one example how they function in a real case example. Based on the symbol of the legend, this symbol is devoted to the manual trip and this symbol is devoted to the level transmitter. Later you can go to my websites, to the videos, to the logic section and download the PDF that I have created and see the legend and see why this symbol is devoted to this one based on the legend I just showed you. So here is the AND group, flip-flop, and the consequences, which is the trip or a stop of the pump. As you can see, the activation of each of these causes are shown by a binary value. For instance, when the operator in the control room pushes the manual trip in the console, the manual trips becomes activated and it sends the signals of on. And if I equalize the on to the value of 0, it sends the 0 value to the AND elements. And the same happens when the level transmitter in the sites shows the value which is below normal value and therefore it is activated and sends the low value, and since I equalize the low value to the 0 binary value, it sends the 0 to this AND element. But you might wonder and ask this question, why didn't you choose 1 instead of 0 for these elements? Don't worry, I'm gonna explain why I chose 0 instead of 1. At the end of this descriptions, at the end of the description of this logic diagram, we're gonna find out. Just stay tuned and wait. So how it works? Imagine that everything is normal condition and suddenly an operator pushes the manual trip. So it sends that the manual trip becomes activated and it sends the value of, since I set the on to the 0 value, it sends the 0 value to these sections. So here becomes 0. But how about this line? How about this input? Maybe the level was in normal conditions. So when it is in normal conditions, this part is 1. It just sets the value of 0 when the level reaches the low value, the low level. Therefore, the value for normal condition for this part is 1. And what did I say when I was explaining the AND element? I said that I can get the output of 1 out of this one AND element. I can get the output of 1 out of this AND element when both of these inputs are 1. But when just one of them becomes 0, the output would be 0 regardless of other elements. This one is 1, but it doesn't matter. Since this one is 0, the output becomes 0. So if I want, so both of them should be 1 so that I would get the value 1 here. And in this case, since one of them is 0, the output would be 0. And how about this negation? It goes to the flip-flop. It is right that it is pronounced like this one. Let me write flip-flop. flip-flop. When it reaches the flip-flop, but before reaching the flip-flop, there is a negation here. What did I say about negation? I said that it reverts to the value to another binary value. If we have 0 here, the output becomes 1. And if we have 1, the output becomes 0. Here we have 0, then the output becomes 1. But I said about flip-flop that when the output is directly from this side, the output would be 1. But in this case, as I stated earlier, when the signal goes down, it changes the binary value. Therefore, if it was in this way, the value, the output of this flip-flop would be 1. But since in this case, this line, the red line, is not drawn, and instead the line is drawn from reset 1, it goes down and the value changes to 0. Then here is 0 signal is sent to all elements, to final elements in the substation. And if in substation I set the stop to the 0 when I receive the 0 from control room, the 0 value trips the pump. Why? Because in substation I set the stop to the 0 value. What does it mean? It means that whenever I receive 0 from the control room to the substation, please trip the pump. So when I receive 0, it trips the pump. And here, that's the reason why I chose 0 for these values, because based on process safety, it is better for the contactor element in the substation to be set to the 0 instead of 1, because 0 is more safe based on the documents and the experience. This was the procedure that shut down the pump during emergency situations and drives the pump and pushes the pump to go to the safe position in order to prevent or preclude any consequences, unwanted consequences. Now let's see how this logic diagram functions during normal operation. In normal operations, I'm going to show all of these values with green colors. In normal operation, since everything is normal, neither manual trip or low level is activated, which means the output of these boxes is 1 in normal condition. So in normal conditions, both of these values are 1. As I have stated, since both of these inputs are 1, therefore the output of an element would be 1 because both of these inputs are 1. When it reaches the negation reverses the binary value of 1 to 0. So I'm going to write it here. And as I just said, since it goes down, instead of going directly out of this one, it goes down and the binary value of 0 becomes 1. So the binary value of 1 is sent to the substation. And in normal operation, neither of the pumps are tripped or shut down. Why? Because in substation, I set the stop value to the 0. It means that whenever I receive 0, please trip or shut down the pumps. But here I receive 1 for both pumps, which means that the substation doesn't have to trip or shut down the pumps. That's the reason why during normal operations these pumps are not tripped or shut down. And I think so far you have understood how it works. But as I promised, I said that I will explain the function of resets in logic diagram. Imagine the situations. Imagine the first scenario that a process operator in control room pushes the manual trip or another cause. We have low level in reflux drum and the pump is tripped. Now after 20 minutes, after 10 minutes, the operators in the control room revert all of the situations into normalcy. Revert the situation, the condition into normalcy, and everything is in normal conditions. And as a process operators, right now, I wanna start the pumps. By the way, the value I set for the time that operators try to revert the situation into the normalcy. For instance, I said 10 minutes or 20 minutes. These are just, just for training purposes. Sometimes these values are proved, sometimes this value proved to be fatal, and operators must think on their feet and act quickly in order to return the situation to the normal condition and start the pumps so that it wouldn't cause any detrimental consequences to the plant. So here everything is in emergency situations. The operator has stopped the pump and after a period of time the operators makes everything normal. For instance, uh, the levels goes beyond the normal conditions and all of this becomes one and one. But remember, in the history of the substation, we have 0 as the signal. As I said, in emergency situations, the 0 signal is sent to the substation and therefore trips the pump. And whenever operator makes everything normal and they push the start of the pump, they can start the pump. Why? Because in the history of the substation, we have still 0 as the input from the control room to the substation. We have to remove the 0 from the history of the substation. That's where reset comes to the game and plays an important part. How? Imagine that as an operator, I've revert all of this abnormality to normal conditions, and all of the signal from these ones are value are 1 and 1. I create the reset here and activate the reset. I press the resets, and the on is created. The reset becomes on, and I equal on to the value of binary value of 1. So here I'm going to choose another color. So when I press this once, the on value becomes 1. I want to show you how it functions. So by pressing this one, I send the signal of 1 to this one, and here before the flip-flop the value is 1. As I said, in flip-flop, when the output line is directly from the input line, like this one, the output would be 1. But if it goes up, the value changes to 0. Here, for instance, the value goes down and changes to another value. I want you to fully understand the concept behind flip-flop. So since it goes directly, the value would be 1. And as a result, it sends the 1 value to these ones and these ones, and changes the history of the substation from 0 to value. What does it mean? It means that the solenoid, the energizer of the pumps, now can be started and drive the pump. Now we have other elements such as maintenance override switch. Sometimes during operations, we need some maintenance on transmitters. For instance, 2 of them are indicating correct value, but one of them is showing a fallacious value, and the instrumentation teams from maintenance personnel have to work on this in order to correct the transmitter. But if I as process engineers, process operator, provide them the access to this one without changing anything, the low value is gonna be activated and it's gonna trip the pump. While everything was in normal condition, the level of the pump, the level of the reflux theorem was in normal condition. I just wanted to change to correct one of the transmitters. For instance, we have 3 transmitters, level transmitter, and one of them is showing a wrong value. But it was in normal conditions, so it trips the pump in a wrong way. So how can I prevent such occurrence? I can use maintenance override switch and place it here and activate it so that such trips would be prevented. For instance, if I want to work on one of these simultaneously, the moment I start working on this as instrumentation or maintenance engineer,
I start working on this, it's gonna send the signal of zero. And as I stated, when one of these becomes zero, this pumps and this trips the pumps. So I create a maintenance override switch as a barrier and don't allow the zero value to pass this barrier and trip the pump. That's the function of maintenance override switch. And I stated that before in interlock diagram, the function of delay, I set the function of delay to prevent the fallacious value indicated by some of the transmitters while everything is normal conditions, and it is the symbol of delay in logic diagram. I think I have uh, given instruction about all parts of the logic diagrams and in a comprehensive way. But in order to make you better understand and help you stand on your own two feet to be able practically to create such logic diagram, I'm going to provide you with another important examples which is typical for all of the refinery and petrochemical plants, which is BFW pumps, boiler feed water pumps. The function of boiler feed water or BFW pumps is to provide BFW to the steam drums, to the boiler and a steam generator, so that adequate amount of steam would be generated in boilers or superheaters, and therefore these pumps plays a crucially vital and important part in petrochemical and refinery plants. And these pumps are the most important pumps in petrochemical plants, and requires high drivers, high amount of powers. In plants which produces high amount of steams, normally we have three BFW pumps, two of which are driven by turbines and one of which is function as a standby and is driven by a motor rather than by turbine. And as you can see here, we have a deaerator. The function of deaerator is to deaerate the BFW, the demineralized water. It helps to remove some oxygen from the demineralized water and in a mechanical way, and of course some parts of the oxygen is removed via chemicals. So the function of the aerator is to lower the amount of oxygen content in the demineralized water stream, and the water which uh, exits this drum is called boiler feed water. Here is the demineralized water and here is the boiler feed water. And let's see how we can create interlock and logic diagram for such pumps. Like other typical pumps, it has two causes. Of course, in fact, it has three causes, but two causes are typicals for all of these pumps, which consist of manual trip and low-level in drum, regardless of the kind of drum. But sometimes it is reflux drum, sometimes it is deaerator drum, sometimes it is a separator. Regardless of the drum or the type of the drum or the function it has, low level is one of the causes of the pump trips. Or another, as I explained in the last example, was the manual trip, which is decided by the operators in control room. But since These pumps are extremely important to process engineers. We add another cause, which is the pressure at the suction of the pump, so that any damage to the pump would be prevented. This pressure at the suction of the pump, or suction pressure, should not reach a minimum value. So I need to create three interlocks for pump A, pump B, and pump C. But remember that the cause of low level in the aerator for all of them is the same. Therefore, in order to prevent the rewriting of the cause of low level for all of these pumps in their interlock, I create another interlock as which means the low level in the aerator. So I have four interlocks. If I choose, for instance, to show the low level for all of them, it is also correct. That's not a problem. But sometimes I want to make my documents seem more beautiful. I can prevent rewriting of low level as the cause for all of these interlocks. Instead, I create another interlock, another IS, and which shows the low level in the drum. So the IS which corresponds to pump A is 71, 72 to B, and 73 to C. And I create IS7 70 for the low level in the deaerator as I explained. So here, if here we need a manual trip for all of the pumps and the low level and the delay time, which is typical, and here are the consequences, which stops this one. These signals are sent to the each of the pumps IS group. So suppose that I want to create the IS for interlock diagram, interlock IS for pump A. I say that it has two causes. The first cause is IS70, which is the low level in the deaerator plus the manual trip, which I showed here. And another cause is the low suction pressure of the BFW pump. And of course, as I said, since it is a transmitter, I need to add a delay time so that to prevent any fallacious indication. So it has two inputs.
Hi, I'm Mohammadreza Behrouzi, the manager of Educational Institute for Equipment and Process Design. I hope that you have enjoyed every moment of this video. I highly recommend you watching videos instructing chemicals from our websites or through our YouTube channel. By watching these videos, you can become not only familiar but also a professional in chemical designs for boiler and cooling water systems. So far, if you have enjoyed the video, hit the like and subscribe.
As you can see, here I have a manual trip, but you might say that you have added manual trip for IS70. Why did you add manual trip for these ones? The function of this manual trip is different from the function of this manual trip. If I press this manual trip, it it trips all of the pumps. But if I press this manual trip, it just trips this pump A, not other pumps. They are in running status. And when one of these activates, it activates the IS-71 and therefore trips or stop the turbine. In this case, stop the turbine, and for pump C, stops the motor of the pump. But you see some RB here and RB here. What does it mean in interlock diagrams? Let's go through the legends. If you see P in interlock diagrams, it means pulse signal. If you see D, I explained that action delayed adjustable 0 to 10 seconds. If you see manual trip, manual activation of IS units, R means manual reset of IS units, and RB that we are looking for. Final element to be reset on control panel after reset of IS units. Final element to be reset on control panel after reset of IS units. What does it mean? It means that you have made all of the causes to IS-71 normal, and now you are supposed to start the turbines. But you should go to the panel of the turbine, reset the turbine so that you can start the turbines, and all of the conditions are in good conditions. Now let's go through the logic diagrams and how we can create the logic diagram for IS-70 and 71. Remember that IS-71, IS-72 and IS-73 are similar, and therefore we just gonna go through IS-71 and IS-70 logic diagram. For IS-70, the causes are manual trip and low level in diameter. We have delay here and three following actions, three consequences, which is the stop of pump ABC or IS-71, 72, 73. We go through its logic. Here, the logic diagram is exactly like the last logic diagram that we investigated. Here is the manual trip and low level in the diameter. I explained comprehensively and thoroughly the last logic diagram how this binary value of 0 works, and how this negation, how this AND elements and flip-flop works. So it is exactly like that one. So 0 goes through this AND group when one of these activated, and after negation it becomes 1 and it goes down, and uh, the binary value of 0 is created and is sent to the other end user. Which one? IS-71, 72 and 73. And how about IS-71? You can see that it has the AND group. The difference between the last logic diagram and this one is that this AND group has three inputs instead of two inputs. Here we have the manual trip for just that pump, and here we have the signal from IS-70 from last page, and here we have the signal from suction pressure, and it goes through the AND element, and after passing the AND element it goes through the negation and flip-flop, and finally the signal is sent to the driver of the pump panel. So I'm just gonna give you one more example of to know that how sometimes it would become complex for some pumps to create logic and interlock diagrams. But before going to that sections, I want to make sure that you have fully understood these logic diagrams. Imagine that this suction pressures goes below a set value. It produces, since it goes below set value, the low value of suction pressure is activated, and we set the low equal to zero. Therefore, zero is passes through this line, and as I stated, when one of the input to the AND element becomes zero, the output would be zero. And after and passing through the negation, the zero becomes one, and it goes to this direction, goes down, and the one binary value of one becomes zero. Therefore, the zero value from this signal is sent to the energizer of the pump, and it stops the turbine. These were two typical examples for typical pumps used in petrochemical and refineries plants. But sometimes it would become extremely complex, especially for package of compressors. These examples I have shown and investigated this example in my package of interlock and logic diagrams. You can go to my website and watch this package. In that package, I explain every aspect of this logic and interlock diagram for this one. As you can see, if you look at the picture of the logic diagram, you see that how it would becomes complex for such pumps. Of course, it is not just one page, it has 3 pages for just two pumps, because the consequences, the causes in compressor package is much more complex than a simple process units. You see, 3 pages just for two simple pump in a compressor package. Of course, the logic diagram that I just showed you are for a large compressor used in methanol plants, and the package of the compressor is really large. Therefore, and by the way, the logic diagram has about 300 pages, 300 complex pages with different logic diagrams for different equipment. Sometimes it is as simple as the two example or typical example I showed you, and sometimes it becomes extremely complicated, like the logic diagram that you are just watching in this video. And of course, for lube oil pumps, there are some logic diagram. You can see again that how complex it would become for such pumps. You can go to my website and download this PDF for different pumps with different function and how they could be created. It is the end of our sessions for uh, rotary equipment such as pumps, and of course you can go to our website and the watch other videos which has been devoted to the instruction of interlock and logic diagram for other equipment such as fire heaters, separators, or turbines. By watching these videos, you become a real and practical process engineer you wished for in the past. I hope that you have enjoyed every aspect and every moment of this video, and you would be able to use this instruction for your application. Like always, I wish you a bright future and enjoy your life.